So all of these factors are going to go into what's called a rate law. And a rate law is like a law, if you will, an equation that's specific to a given reaction. And it tries to help chemists and scientists to figure out things that make the reaction go faster and slower, and also perhaps provide ideas on how the reaction can go faster or slower. Now, you must determine the rate law experimentally, all right? Despite all the AI and supercomputing kind of stuff that's available now, rate laws must be determined in the lab, all right? So this is a lab-based phenomena, which is kind of cool. And the rate of a reaction will be proportional to the concentration of each reactant raised to some kind of power. And I'm sure that's not super clear, so I'll give you some examples of that. So the rate law is an important tool to figuring out why reactions go fast and slow, and also to provide some ideas about how to make them go faster and slower. So for a random reaction of capital A going to products, where capital A has a stoichiometry of little a, you can write a general rate law like as follows. The rate equals the rate constant K, which is also something you have to figure out through experiment, times the concentration of capital A to the n power. And n is called the order of the reactant. Now for Chem 222 and Chem 223, n is going to be 0, 1, and 2 only. All right. Outside of these classes, you might see different values for n, but in our classes, it's going to be 0, 1, and 2 only. So if you know the rate order and you know the rate constant K, then you can find the rate, the speed of the reaction for any set of combinations, which is really cool. And only reactants and sometimes catalysts will appear in the rate law, no products. So this is kind of the basis here of determining what goes on. So here's what's going on. The rate is the speed, all right? And you can measure that by figuring out changes of concentration over time, stuff like that. But to know why that speed is as it is, it's nice to know about the order of the reactant. That makes a big difference. And you do need the rate constant K. K is a value that's independent of concentration. It does change with temperature, but rate constant Ks are just numbers, and we'll talk about how to do all of this here in a little bit. In Chemistry 222 and Chem 223, those orders will be 0, 1, and 2 only, and they call them 0 first or second order or zeroth. I don't really like that term, but that's what they call it. But anyway, the effect of 0, 1, and 2 is just like in math. So anything to the 0 power, like 3 to the 0, 10 to the 0, anything to the 0, is just 1. So any reactant to the 0 power will just be equal to 1. Rate equals K, the rate constant. What we're going to see a lot of, though, are first order reactants. Now, anything to the first order is just itself. So as an example, 2 to the first power is 2, 10 to the first power is 10, etc., etc. So rate equals K times A. That would be a first order reactant. We will see some second order reactants, though. Second order reactants affect your rate in a big time way. It's like in math. If you have 2 to the second power, it's like 2 squared, which is 4. So you double the concentration and the speed goes up by 4. If you were to take 10 to the second power, 10 squared is 100. So if you raised it by 10 times, the rate would go up by 100 times, etc., etc. In other classes, you might see different orders, but in this class, you're only going to see 0, 1, and 2. So let's look at this reaction, 2 NOs and O2 making 2 NO2s. They found that the rate order for that equals K, rate constant, times NO squared times O2. So we would say that this reaction is second order with respect to NO, because NO has a 2 by it. It's first order with respect to O2. There's not a 1 right there, but it's implied. And also, if you hear about overall rate order, you just literally add up the individual orders. So 2 from NO and 1 from O2, 2 plus 1 equals 3. The overall rate order would be 3 if you hear that expression. In this class, reaction orders 0, 1, and 2 only. So let's talk about what those mean a little bit more. If you have a zero order reactant, then anything that you have for A, then A to the 0 power will be just 1, and rate equals K. So let's say you were going to double the concentration of A, but A is a zero order reactant. Well, doubling to the 0 power is 1. Rate is still going to equal K. So if you have a zero order reactant, it doesn't affect the speed of the reaction at all. And we'll come back to that later. First order is very common for reactants and catalysts in a rate law. And those have a first order dependence. So anything to the first order is itself. So 2 to the first is 2, 10 to the first is 10, etc., etc. So if you would happen to double the concentration of A and its first order, the effect on the speed would be like 2 to the first power. It would be twice as fast. So you double the concentration of A, the speed goes up by 2. You triple the concentration of A, 3 to the first is 3, the rate is going to go up by 3. So that's kind of the idea there. If you happen to have a second order reactant, and they do exist, they're not real common, but they do exist, the rate just goes crazy when you start changing concentrations. So remember that anything to the second order would be like A to the second power. So if you double something, that would be like 2 to the second power, or a change of 4. If you had it 3 times as much, then 3 to the second power would be 9. You'd have 9 times as much. So you'll see huge changes to the rate if you have a second order reactant. So just FYI on that. To find the orders of reaction and then eventually K, what scientists usually do is they'll change the reactant without changing the other reactant. So they'll change like one reactant in a reaction without changing the other reactant. And they'll monitor the effect on the speed or rate of the reaction. If you change just the initial concentration of one reactant, then you can figure out the effect on the rate to figure out the orders. So the first part of this process will be to find the orders of the reaction. And again, for us, it's only going to be 0, 1, and 2. Once you have the orders of the reaction, then the last thing you can do is find the rate constant K. And K is independent of concentrations. It does depend on temperature, as we'll see, but it doesn't depend on the concentration, so that's why we leave it for last. Here's some examples where we have NO2 and CO reacting to make something. Who cares? All right. But I want you to look at what's happening. Up on the right-hand side, we essentially have 3 trials. There's trial 1, which is when the concentration of NO2 and CO are both 0.10 moles per liter, and the rate on the far right, 0.0021. But then we have trial 2. And notice how the NO2 went up by 2 times. It went from 0.10 to 0.20. Likewise, though, the CO concentration stayed the same. It did not change. So any effect on the rate, the value on the far right, will be a reflection of the NO2 on the left. So if we doubled NO2, we went from 0.10 to 0.20. Then we're going to also look at how the rate changes on the right. And you can see that 0.0021 to 0.0082, that's a change of 4 times. So for NO2, you can visualize it then as changing the concentration by 2 to the x, that's the order, we don't know the order yet, but 2 to the x equals a change in the rate of 4. So 2 to the x equals 4, x is going to be 0, 1, or 2, x here has to be 2. And that's how they found the NO2 squared part down there at the bottom. The doubling of NO2 resulted in a rate change of 4. 2 to the x equals 4. X is going to be 2. But let's go on to the next one, because in the 2 versus 3, the third set of reactions, they left the NO2 alone. They didn't change that. You don't want to have any effect from the NO2. But they doubled the CO. CO went from 0.10 to 0.20. And if you look on the right-hand side for the rates, it went from 0.0082 to 0.0083. That's almost a 0 change of the rate. It almost stayed the same. So as you double the rate, the speed stayed the same. That would be like 2 to the x equals 1. And remembering that those little x's, the orders are only 0, 1, and 2, that means that CO here has to be a 0 order reactant. So again, to find these orders, you want to change one reactant and leave all the other reactants alone. And as you change one reactant, you look for the change in the rate. So doubling NO2, the rate went up by 4. 2 to the x equals 4, x is going to be 2. We did the same thing for CO in 2 versus 3. We left the NO2 the same, so there's no effect on the speed from the NO2. On the other hand, the CO went from 0.10 to 0.20, that's doubling it. So 2 to the x in that case equals 1. There was no effect on the rate. X is going to be a 0 order reactant. Once you have the values of the orders, so in this example, we saw that NO2 was second order and CO was a 0 order. And remember that anything to a 0 order is just 1. So in this case, I just totally ignored CO to the 0 power because it doesn't matter. Rate equals K times NO2 squared. And you can use any of those sets of data, 1, 2, or 3, to figure out what K is going to be. So in this example, I used the first set of data, and you can see that the rate in number 1 was 0.0021, NO2 was 0.10 in trial number 1, and we're squaring it because it's a second order reaction. So K equals rate over NO2 squared, rate constant K, 0.21. The units on this particular K would be inverse molar, inverse seconds. So that would be liters per mole seconds. And that's fine if you wish to report the units. A lot of times, though, the convention is just to ignore the units of K. So I would just ignore them. But if you want to, you can absolutely figure it out. Look at the chemicals that go into figuring out the rate constant K and go from there. But hopefully this gets you an idea not only to how to find the orders, but also then how to find the value of the rate constant K. Here's an example. We have a compound called ethanal. Ethanal is an aldehyde. You don't need to worry about that, but aldehydes do sometimes break down. In this case, it's breaking down into CH4, which is methane, and CO, which is carbon monoxide. And we have here some rate law data, all right? And you can see, like before, trials 1, 2, 3, 4, the concentration of the ethanal, the reactant, 0.1, 0.2, 0.3, 0.4. And on the far right, that's the disappearance of the ethanal. That's the rate of how fast it's disappearing. So what we're going to do to figure out this particular rate law in K, we're going to first figure out the rate order of how ethanal is changing. And once we do that, we'll use any set of data. We'll plug in the values to find the value of K. So in this particular problem, what I would do is like what we did in the last example. And notice trial 2 versus trial 1. The ethanal, the reactant, is being doubled. You're going from 0.10 to 0.20. So it's a doubling of the ethanal. And any effect over here on the rate law will be a reflection of doubling the ethanal. And you can probably see that 0.081 divided by 0.020 is roughly a change of 4. The rate is going up by 4 times. Like 0.02 times 4 would be 0.080. It's 0.081. That's close enough. The doubtful digit, the uncertainty, blah, blah, blah is going to happen. So for ethanal, if you want to figure that little order x, it's like doubling it, which is 0.2 divided by 0.1, doubling it to the x power, which we're trying to figure out, resulted in a change in the rates of about 4. 0.081 divided by 0.020 is about 4. And realizing that those little x's, zeros, ones, and twos only, well, 2 to the 0 would be 1, so that's not appropriate. 2 to the 1 power would be 2, and that's definitely not what we saw here. The rate went up by 4 times. But 2 to the second power, 2 squared is 4. So definitely here we have a second order reactant. To formalize this, all right, there's different ways you can do it. Now, these two ways that are described on the left in black and on the right on blue are the two formal ways to do it, all right? You can compare one set of rate data to the other set of rate data. So let's compare on the left-hand side rate 2 to rate 1. And rates, which are the numbers 0.081 and 0.020 for the two trials, they both equal K times the concentration, so 0.2 for rate 2 and 0.1 for rate 1, both to the x power. In this problem, the K's cancel out. K divided by K is just 1. Don't have to worry about it. And 0.081 divided by 0.020 is 4.1. And 0.20 divided by 0.10 is 2 to the x. So if you remember that x can only be 0, 1, and 2, like I said earlier, if x is 0, it would be 2 to the 0 equals 1, and that's not what we see. We see 2 to the x equals 4.1. 2.0 to the first power would equal 2.0, and that's not what we see either. We see 2.0 squared equals about 4.1. So this is definitely a second order reactant. Now in the lab, we're going to use a different method, which is using logarithms. And logarithms can be really helpful here. Notice here, if you do the log of both sides, you get log of 4.1. By the way, this is going right here. So log of 4.1 equals log of 2 to the x. And in the logarithm world, log of 2 to the x can be rewritten as x log 2. So x, which is the order, is going to equal log of 4.1 divided by log of 2.0, rounded up to the nearest number. Log is going to be equal, or x is going to be equal to 2. So either way works great here. Use the way that works fine for you. We're going to use the logarithm method in the lab, but you can use either method is cool. Regardless of which method you use, the order of the reactant, CH3CHO, the ethanal, is 2. All right, so this is a second order reaction. It's second order with respect to the reactant, CH3CHO. In this reaction, we have two NOs and two H2s reacting to make N2 and 2 waters. And this reaction has been determined to be second order in NO and third order overall. What's the rate law for the reaction? Okay, so if it's second order in NO, then we must have a 2 by the NO. And you can see that only answers C and D have a 2 by the NO. A and B, there's no superscript 2 by the NO. Those would be first order NOs. So A and B are flat out, not going to happen. Third order overall means that if you add up all the orders together, it equals 3. So 2 is NO. We don't know H2, but 2 plus whatever H2 is equals 3. That means that the H2 is going to be a first order reactant. So in this case then, if H2 is first order, we would write rate equals K times NO squared times H2 to the first power, or they just leave the first one off. Now, if you happen to pick answer D because of the 2 stoichiometry in front of the H2, this is a good thing to talk about. Those stoichiometries are not necessarily the rate orders. They are sometimes, but not all the times. And we'll talk about this here in a little bit. So rate orders and stoichiometries, not always the same thing. And in this case, they certainly are not the same thing because it's not rate equals K times NO squared times H2 squared. We have instead rate equals K times NO squared times H2 to the first power. And we'll talk about why that is here in a little bit. So use the rate order information. Don't rely on the stoichiometry. So in the last example, we saw that the ethanal, the CH3CHO, was a second order reactant. So rate equals K times the ethanal concentration squared. So it says rate will go up by so much when the initial concentration doubles. Well, if the concentration doubles, that would be like 2 to the second power. The rate would go up by 4 times. And therefore, we would say this reaction is second order. If you put a 2 there, it's second order. If there's a 1, it's first order. A 0 would be 0th order. I don't really like that. I would just call it 0 order, but either way is fine. The last thing we need to do is find the value of the rate constant K. If you look back in the set of data, we started this problem. For experiment number 3, the rate was 0.182 molar per second, and the value of the ethanol was 0.30 moles per liter. At the time, we didn't know the rate order, but the rate order now we know is 2. So the only thing here we don't know is K. So if you want to calculate K, K is 0.182 divided by 0.3 squared, and that comes out to be a value of 2.0. So you can now find the rates at other values of concentrations, etc., as long as you don't change the temperature. If you change the temperature, you change the K, not quite as much fun.